Kia ora koutou, no mai, haere mai. Welcome to lesson 27 for introductory physics. This lesson is going to finish up our section on atomic structure, but we'll actually be looking at radiation in general and then returning briefly at the end to the idea of nuclei that are going to split apart or possibly join them together in a slightly different manner than what we saw for nuclear radiation in the previous lesson. So that's the goal, but we're still including this under the atomic structure section because it is all dependent on the idea of the structure of the atom and how that nucleus holds together and how it decays. So the goals today are: describe environmental sources of radiation and some uses of radiation, describe the health effects of radiation, describe how radiation is measured and detected, and then at the end define very generally fission and fusion and the difference between them. We're not going to go into a huge amount of detail for those. Firstly, photons and radiation. We've already met the idea of photons. Photons are a type of electromagnetic radiation that we're going to discuss further in the final section of this course. All we know so far is that a photon is a tiny little packet of pure energy. It is the same thing as visible light, and it is released by things when they get hot. That's what we've met so far, thermal radiation. So visible light is made of these photons, but so are other types of light, not just visible light. We've also got microwaves, radio waves, ultraviolet light, infrared light, X-rays and gamma rays. And so we've got different types of light that can come out. So visible light is just one of them. And the type of light depends on how much energy there is in the photon. Remember, the photon is a little packet of pure energy, just a little packet. They're tiny, and it's pure energy. And so how much energy is in that little packet determines what type of light it is. And of course, by what type, we just mean what it does to things that it hits, things that it interacts with. And so it makes sense that the different amount of energy would have a different effect on whatever it hits. Visible light photons, they're the ones that our eyes are built to receive, to be able to absorb these visible light photons and provide our brain with information about the world that we see. Again, we'll talk about that a bit more in the last section. Those photons have between 3 and 5 times 10 to the negative 19 joules. So that's between a 3 and a 5 in the 19th decimal place of joules. As you move into higher energy, so you pack more energy into that one little photon, pack more energy in, then you get into ultraviolet. Ultraviolet, ultra being above violet, so more energy than violet. That's all UV means. They do come from the sun as well, but we get them from other sources as well. The energy in a UV photon can be anywhere up to 2 times 10 to the negative 17 joules. Right? Negative 17 versus the negative 19 that we had for visible. X-rays are even more energetic than UV photons. X-rays can have up to 2 times 10 to the negative 14 joules in one little packet of energy, and gamma rays are the most energetic photons, and they can have anywhere above that X-ray limit. I will come back, as I said, to the idea of light and electromagnetic photons in the last section, and we'll talk a little bit more about classifying these types of photons. But for now, what we want to see is that X-rays and gamma rays are much higher energy than visible light. They are fundamentally the same thing. They are fundamentally exactly the same as visible light. They just have more energy packed into each little packet. If visible and ultraviolet light photons come from something being hot, like the sun or a hot stove element, then where do X-rays and gamma rays come from? Where do these come from? Remember our talk about electron levels. So in an atom, we had a small nucleus, the size of a pea in a football stadium, tiny nucleus, and we had electron levels that were where the electrons could orbit. They were sort of like shells. They were actually three-dimensional shells, not like a planet's orbit that's a one-dimensional path or a two-dimensional circle. This is a three-dimensional sphere, and the electron can travel around that, but there are different levels, these different shells. It's a whole bunch of concentric spheres, and the electrons can travel around their sphere, but occasionally they can jump between the spheres. If they get given a bit more energy, there are a bunch of different ways they can get that energy, but if they get it, then they can jump up to a higher level. And it's called a higher level because it needs more energy for the electron to get there. So the electron can absorb a bit of energy from somewhere, and it can use that energy to jump up to a higher shell, a higher electron level, and then it will just do its thing and orbit that. But eventually, it might be quicker, it might take a little while. Eventually, the electron will jump back down to its original shell. It won't stay out in that higher shell for long. The reason it takes more energy to get out to the higher shell is that you're pulling a negative charge away from a positive charge. Remember, negative electrons are attracted to the positive nucleus, and you're pulling it away. Just like our usual analogy of a spring, same thing. The electron is being pulled towards the center, the nucleus, and you're pulling it further away. That's like stretching a spring a bit more. You need to provide a bit more energy. And so you give it a bit more energy, and it does go up to that extra shell. When it jumps back down, it needs to get rid of that energy. That electron is not in contact with anything. There is nothing touching that electron. It's not touching the nucleus. Right? It's not touching some other atom because it's inside this atom. And remember that atoms are bonded to their neighbors, but they're not rubbing up against them. So this electron has to get rid of that energy, but it's not actually touching anything. And so the only way it can do that to get rid of its energy is to just emit it as a photon, a little packet of pure energy, because that doesn't need the electron to be touching anything else. So it emits the energy as a little photon. So when an electron jumps down from one level to a lower level, a level closer to the nucleus, then it will emit its excess energy as a photon. So that's where visible light comes from. That's visible light. Occasionally you'll get ultraviolet or infrared light from those single level jumps, but you can jump more than one level at once. And by you, I mean the electron, not you personally. The electron can jump more than one level. If it jumps 2 levels, then that's more likely to be an ultraviolet photon. If it jumps 3 levels, then we're getting quite high energy ultraviolet photons. But an electron that jumps from the outer orbital of a big atom to an inner orbital, then it's making a huge jump across multiple shells. It's got a lot of energy to get rid of. It's a lot lower energy, really close to the nucleus than it was in its really high position far out. And it will give off all of that energy, again, as a single photon. But that is so much energy that it now becomes an X-ray photon. And that is where X-ray photons come from. They come from electrons of bigger atoms jumping from outer shells all the way to inner shells. So that's where X-rays come from. They just come from that electron jump. But we said gamma rays are even higher energy than those X-rays. And if the electron is already jumping from its highest shell to its inner shell on a big atom, there's no way we can get a bigger jump for that electron. We can't get more energy out of that electron. So clearly gamma rays are not coming from this electron jumping down levels. They're not coming from that same place. Where are they coming from? The answer is the nucleus itself. Gamma rays are released during nuclear decay. So during the alpha and beta decay that we already talked about, that's where gamma rays come from as well. It doesn't change the charge of the nucleus because it's just a little packet of energy. It's got no charge. It also doesn't change the mass because, again, a little packet of energy doesn't have any mass. So it's not changing the charge, it's not changing the mass. That's why we haven't actually talked about it yet, because it does not change the mass or atomic numbers of the nucleus. So we don't need it in decay equations. We don't need it in order to understand that nuclear decay process. So gamma rays, we don't often bother writing them in our decay equations, but they are pretty much always going to be there. Whenever a nucleus undergoes alpha or beta decay, it will almost always undergo gamma decay as well. And that is just the release of the excess energy that is left over because of that change in the nucleus. When a nucleus decays and changes its form somehow, whether that's a neutron changing into a proton or getting rid of a couple of protons and neutrons as an alpha particle, however it does it, the energy needed for that nucleus is now a bit different, and it will get rid of that excess energy by releasing some gamma photons. So that is where gamma rays come from. X-rays, we just, one little comment on that, because people are aware of them, there are a lot of uses of X-rays, but the most common one is still the medical imaging process. X-rays are high energy. High energy photons can travel through soft tissue relatively unimpeded. So they can travel through your skin, fat, muscle without too much hassle. If there's a lot of it, then it might slow down a bit, or some of them might get absorbed, but a lot of them can still travel straight through. But as soon as they hit something denser, like bone or metal, then the X-rays, the photons, are going to be absorbed by that denser substance, by the bone or the metal. And that means that you won't get electrons coming through where there's something dense in the thing that you're taking an X-ray picture of. So what they do is they put a photographic plate behind the substance. So you might, the example there is a hand, so you might have your hand here and there'd be a photographic plate here, and the X-rays are shot in from this side. And the X-rays come in, and if they just go through skin, then they'll still hit the X-ray plate. Right? But if they hit a bone, then they'll be absorbed and no electron will hit the plate where that bone was. And so in that way, wherever the electrons hit the plate, it turns darker. And so where the electrons hit, you get black. Where they don't hit, which is where there was bone or metal, you get closer to white, and a gradient in between. If there's just a lot of meat or muscle tissue, then you're going to get a bunch of the X-rays getting through and a bunch not getting through, and so you'll get a sort of a grey colour. So as you can see, if you look at this photograph here, where there's very thin bits of skin, like the tips of the fingers, almost all the X-rays got through anyway. But where there's bone, a lot of them were stopped, and where there was a decent amount of muscle and fat and just other tissues, then a bunch of electrons get through, but not all of them, and you get a sort of a grey colour. So that's how X-rays work. We're not too concerned with them. We want to know about X-rays. We want to know where they come from, which is the electron levels, and we want to know their relative properties in terms of their strength, their energies, and so on. Again, we'll mention the exact energies and the light boundaries when we get to that section. But I don't expect you to go and learn all about how X-ray photography works and X-ray imaging works for medical purposes. I just thought I'd mention that because it is interesting. So a little bit more about types of radiation. We've added in this idea of X-rays and of gamma rays now, in addition to our alpha and beta rays, alpha and beta particles. But X-rays are not nuclear radiation. Remember that nuclear radiation, the nuclear means nucleus. Right? It means of the nucleus. So nuclear radiation is talking about anything that comes out of the nucleus as a result of radioactive decay. So X-rays don't come from the nucleus, so they're not a type of nuclear radiation. They are still radiation because they are light, they are photons, they are electromagnetic radiation. That is what electromagnetic radiation is. It's just all the types of light and photons. So they are still a type of radiation in that sense, but they are not nuclear radiation because they have not come from the nucleus. Right? If photons come out of the nucleus, they're always going to be higher energy, and they're always going to be gamma photons. When we're talking about radiation, we often use the term ray to refer to a stream of radiation particles. So if a single atom undergoes radioactive decay and emits an alpha particle, then that's just one helium nuclei, one particle that flies off into space. But if you have a substance made of millions or billions of these radioactive atoms, and they're all undergoing this radioactive decay, remember they'll do it randomly because of the half-life. They'll just randomly, some will decay, and then next moment a few more will decay. So you get this constant stream of alpha particles coming off this block of substance. And so that constant stream of alpha particles coming off a whole big sample of radioactive particles, that's called an alpha ray. So an alpha ray is just a constant stream of repeated decay particles. A beta ray, same thing, a whole stream of energetic electrons coming off nuclear decay from a whole big sample of multiple atoms. And finally, gamma rays, exactly the same, but now it's just the photons that come out when that nuclear decay occurs. So generally, you'll get either alpha or beta, and then you'll get gamma with one of those other two. As we've already been doing, a single one of those particles is just called a particle. So an alpha particle is a single energetic helium nucleus, a beta particle is a single energetic electron, and a gamma particle is a single high energy photon. Remember that these only apply when the particle is the result of nuclear decay, when it's come from a nucleus. They are not names for every helium nucleus and electron. Even if you get a high energy helium nucleus, if it hasn't come from a nuclear decay, then it's not an alpha particle. Because they have different masses and different energies, the different types of radiation have different penetrative abilities. That means they can go different distances through different materials. Alpha particles are quite large. They are helium nuclei. They've got 2 protons and 2 neutrons. That's quite a lot of mass. It's quite a lot of mass. Even if they are highly energetic, that's still a big object. And a big object, that's the same size as a helium atom, essentially. A helium nucleus it's not going to be the same size because it's the nucleus, it's the P out of the middle of the football stadium, but it's still big and it's got a lot of mass, and it's got 2 positive charges, so it's got a decent amount of charge, decent amount of mass, and if you fire that into some substance, it's going to hit something fairly easily. It's going to hit something. And so the alpha particles are actually stopped relatively easily. A thick sheet of paper, a layer of clothing or 2, that's going to stop alpha radiation. So alpha radiation is pretty easy to stop. Beta particles, though, they are tiny, tiny electrons. Remember, we said that electrons are tiny even compared to the nucleus, compared to a whole atom, even smaller again. But compared to the nucleus, they are tiny, so they are not as likely to hit something as they fly through. Remember, we said how big the atom is and how tiny the nucleus is, which means most of that is just empty space. So if you've got a substance, even if it's made up of atoms all the way through, a lot of that substance is going to be pretty much empty space. And that tiny electron with a lot of energy that's just flying through is not very likely to actually hit something as it travels through. So you need a bit more, right? You could have a couple of layers of atoms and it would get through quite easily. You need more atoms, more stuff in the way to make it more likely that that little electron will hit something and be stopped. So it can be stopped by something a bit denser like aluminium. Metal is quite good because remember, metal shares all its electrons, so they've got the sea of electrons that are flowing through the metal, which means there's sort of stuff everywhere rather than big gaps between the atoms. So metal is quite useful in that sense. So you fire a beta particle through paper or clothing and it will get through. You fire it through a sheet of aluminium and it's going to stop most of the time. Gamma particles, though, gamma particles are photons. They have no mass. They are just a little packet of energy. And that makes it even easier for gamma particles to get through matter, through substances, just fire straight through. Sometimes they might even hit stuff on the way, but they can still just go through because they don't have mass. They're just a parcel of energy. And if they don't hit something and get absorbed completely, then there's still just a little packet of energy that's just going to keep flying through. So it's very difficult to stop gamma particles. And that is where the idea of lead-lined stuff comes from. Gamma particles need a couple of centimeters of solid lead to be likely of stopping. Right? So that's where the idea of lead-lined rooms or bunkers or boxes comes from to stop radiation. We're talking specifically about gamma radiation. Right? You need a couple of centimeters of solid lead. Lead is nice and dense. And so it's lots of matter packed into one space, which makes it more likely for that energy to be absorbed as the photon travels through. So different penetrative abilities, and that means that the risk from the 3 different types of radiation for us as living things is quite different. As we've seen, some terms require more care to avoid ambiguity. Right? This isn't new for this radiation section. We've seen it right through the course. And radiation is another one of these terms. We've already talked about this just a couple of slides ago. We've met thermal radiation, that is electromagnetic radiation or light waves coming off things which have a lot of internal energy, a lot of temperature. We've also met nuclear radiation, which is the idea of alpha, beta, and now gamma particles being released by nuclear decay, by a nucleus which is changing fundamentally. Thermal radiation is obviously related to electromagnetic radiation, which is light. So it is the emission of electromagnetic radiation due to the temperature of the emitter. Just like we've been talking about, alpha, beta, and gamma particles are only called that if they come from nuclear decay. Thermal radiation is only called that if it comes from an object as a result of it having thermal temperature, having thermal energy. So that means that not every photon is going to be thermal radiation. Right? They're all electromagnetic radiation, but they're only thermal radiation if they come from a substance due to its excess, or not excess, but due to its temperature. Nuclear radiation is either electrons, helium nuclei, or photons, and again, only called nuclear radiation if it's a result of nuclear decay. So that means that you have to be careful when you're using this language around whether a specific particle or a specific photon is a nuclear result of nuclear decay, a result of thermal radiation, or wherever it comes from. But a photon will always be electromagnetic radiation. Right? Electromagnetic radiation is photons. That's what it is. So any photon is called electromagnetic radiation. But alpha and beta types particles, they're not thermal electromagnetic radiation. They are nuclear radiation, but they are electrons and helium nuclei. So it just takes a bit of practice, a bit of getting used to these terms and understanding which particles and photons and things they apply to and which they do not apply to. Radioactivity, as we said, encompasses basically everything. The spontaneous nuclear decay of materials as a whole we called radioactivity. Whenever that occurs, you will get one or more of the three types of nuclear radiation discussed, usually either alpha and gamma or beta and gamma. Those are the most common. Humans did not invent radioactivity. Right? This is something that's, again, just language, but also some people get tripped up on the idea of where it came from. It just exists as a fact of nature, of the universe, of the way that atoms are constructed. As long as atoms have existed, so as long as stars have been around to build things bigger than hydrogen, radioactivity has existed. Right? So we did not invent it, we harnessed it, we discovered it and analyzed it and studied it and then figured out how to harness it and use it for our own purposes, but it has always existed. We hinted at this already, radiation and life. What effect does radiation have on living organisms? And that includes us, it includes humans. We are often aware that radiation is dangerous, right? The idea of radiation being a risk, but how much radiation is there and what actually constitutes a risk is not very common knowledge. Where does radiation go? Radiation is small particles of different types, electrons, helium nuclei, or gamma photons, coming from the nuclei, or if you include X-rays, they come from the electrons around the nucleus as well. As I said, that's not nuclear radiation, but it is still a type of radiation and it does still pose a health risk. So we often lump that in with nuclear radiation when we're discussing this kind of radiation and health risk. So these particles, which are electrons, alpha nuclei, and both gamma and X-ray photons, they fly off into the surrounding environment, traveling until they hit something. Remember our discussion about thermal radiation. It flies off as a result of being a bit too hot. It gives off some energy. As a photon, flies off until it hits something and it's absorbed by that thing, and that thing just gains that thermal energy. The same thing happens here. These particles fly off until they hit something and lose their energy. Right? The electron is still going to be an electron, the alpha particle is still going to be a helium nuclei, but they're going to lose that energy they have because they have a lot of energy when they're ejected from the nucleus. The photons, the gamma and X-ray photons are obviously they are pure energy, so when they get hit and absorbed, they disappear. They have turned into energy, which is now inside the substance that they hit. So that energy will just be absorbed by something that they hit. If they hit a living organism, then that big amount of energy that suddenly is absorbed by that cell can cause damage to the cell. And it is very similar to thermal burns. Remember we talked about burning. If you put your hand onto a stove element, please don't do that. If you do, then the thermal energy from the stove element will be absorbed by your skin cells. The skin cells will rupture and die, the proteins will denature, and all sorts of damage will occur, right? And it can kill a whole bunch of your cells. The damage is pretty similar, and radiation damage is often referred to as radiation burns for that reason. It's the same idea. Your cells, your DNA, all your particles that make up you are receiving too much energy and they are destroyed. They can no longer carry out their function. So radiation burns is what we often refer to them as. The difference, of course, being that thermal burns come from the outside, they hit your skin and they will do damage that way. And so if you apply enough thermal energy, you could burn through the skin and get to the muscle and the inside of the living organism. But if you have radiation burns, the radiation can get anywhere through your body. Remember that gamma rays can penetrate up to a couple of centimeters of lead. That means they can get right inside your body, they can get to your internal organs, and they can cause burn damage inside you. And so that's why radiation burns can pose a very different risk to thermal burns, even though they are very similar sort of processes. If the energy is high enough and the damage is bad enough, then the cell can die. And that's not great, but it's also not that big a problem because our cells are constantly dying and they are constantly being replaced and they are constantly regenerating. So cell death from radiation isn't actually a big concern unless a lot of cells die at once. How many? How much radiation do you need to cause concern? We'll come back to that in a moment. First of all, though, let's think about the damage that can occur without killing the cell. Inside our cells, we have DNA. DNA is the instructions for building all of life, so all of us. And if the energy damages that DNA but doesn't kill the cell, then it can result in a genetic mutation. Most of the time, these mutations are pretty harmless. A genetic mutation just means that the code that the DNA has in it has changed slightly somehow, or maybe significantly somehow. But that's often pretty harmless because we only use less than 2% of our DNA regularly, like all the time. So less than 2% of our DNA constantly. Possibly, there's still research and discussion around how much exactly is useful and how much we use, but possibly up to another 20 or 30% on occasional use DNA. But it still leaves the bulk of our DNA being essentially junk. It's not used in the instructions for building us. So if a mutation occurs in that junk DNA, not really a problem. If it occurs in the DNA that we use all the time, that can be a problem. And sometimes that change can just cause the cell to die, the same as if it was killed initially by the energy. And again, not a big problem, but sometimes that genetic mutation can occur in the codes that tell the cell when to stop reproducing. So cells reproduce, they just duplicate themselves, they copy themselves using resources from the body. And if the DNA code that says, okay, make a copy of yourself and then stop copying yourself, if that stop copying bit breaks, then the cell will still copy itself because that code's fine, but it will never stop copying itself. And that's what cancer is. Cancer is just damage to the stop copying yourself code, right? That's all it is. And so cancer happens as a result of that. Just as a little side note, cancer is forming constantly all the time in everyone, but usually our bodies notice it and get rid of it and kill it. So most of the time you've got at least a couple of cancerous cells here and there, but they are destroyed and gotten rid of without hassle. It's only if that code mutation occurs and your body doesn't get rid of that cell quick enough, then it can form what we call actual cancer and need treatment. Since cells can often repair damage from radiation, the time over which radiation is applied is an important factor. Right? It's not just how much radiation you get, it's how quickly you get it. If you get a tiny amount of radiation one day and it kills a couple of cells and your body fixes them, and then the next day you get a tiny amount again and your body fixes those again, and so on for a few days, that might be fine. But if you take all of that radiation, say that happened every day for a couple of weeks, and you have no problem, you never even notice that there's any radiation damage because your cell just gets rid of the problem straight away. But if you take all of that radiation and you apply it all at once, then you might kill too many cells all at once and you might actually suffer some health consequences. So it might be same amount of radiation, but the duration is different. So duration of radiation exposure is very important, not just how much radiation there is. So radiation can present a non-insignificant risk. It can be dangerous. As scientists, we like to quantify these sorts of risks. We like to come up with scales and numbers that can represent them so that we can understand when something is a risk and when it isn't. For radiation, we measure the radiation in terms of rads, R-A-D-S, rads. 1 rad is equal to 0.01 joules of radiant energy absorbed per kilogram of tissue. Right, so 0.01 joules, so 1/100th of a joule per kilogram of tissue. So the mass of the living organism that is absorbing the radiation will change with the amount of energy that is being absorbed. Right, so rads takes both of that into account. So a 100 kilogram human absorbing 1 joule of radiant energy has experienced 1 rad. but so would a 1 kilogram, I don't know what's 1 kilogram, a bunny rabbit, 1 kilogram bunny rabbit absorbing 1/100th of a joule. That would also be 1 rad. So you need to take into account kilograms of the living organism and the amount of energy in order to calculate rads. The amount of radiation that can be done, damage that can be done due to the radiation, depends on the type of radiation that the tissue is exposed to as well. Right? So what type of radiation? We said alpha particles, they can stop by just a thin sheet of paper. So that means that they're only going to get into the very outer layers of skin. They're not going to get very far. There's no way that an alpha particle could damage your internal organs. So alpha particles, right, not going to get very far, but they are big. Right? Alpha particles have heavy mass. Remember, they're in helium nuclei. That's a huge amount of mass compared to an electron. And as we said, gamma and X-rays have no mass at all. So they have a lot of mass, which means they have a lot of momentum, a lot of kinetic energy, and that means that they are going to cause quite a bit of damage on that outer layer of skin. Beta and gamma particles can travel further, but as I said, they have less mass. But we've got different types of damage being done, but we're concerned with the overall amount of damage being done. So even though alpha particle is external and the gamma and beta is internal, they can still both do serious damage. If you inhale or ingest radioactive particles, then those emitting alpha particles are now really dangerous because they have a whole bunch of mass. As I said, they can do a lot of damage, and now they're inside you. Right? Now they're inside, and they can get into the stomach lining and the internal organs that are really close to your lungs and your stomach and cause all sorts of damage. So really, really dangerous if they get inside you. But gamma and beta rays, they could already get inside, and in fact, if you inhale them, then they're quite likely to just travel completely out of you anyway and not even do much damage. So again, different risks for the different types of particles. I don't expect you to memorize all of this, but knowing the different types of particles, their different masses, and the fact that they're all highly energetic and how far they can penetrate, you can pretty much figure this out anyway. So we've got this idea of rads, and we've got these different types of particles, but the damage that it can do to a human depends on the type of particle, right? So not just on the rads, not just how much energy, but which type of radiation is providing that energy. For alpha radiation, that damage is actually greater. As I said, big mass can do a lot of damage, although often just to the outer layer of the body, but it can easily get inside us if we inhale or ingest radioactive particles. And so in the case of like nuclear meltdowns, that can be a problem. So to measure this damage, this risk to us, this health risk, we have to take into account that type of radiation. And that results in something called the REM, R-E-M, which is from Rontgen Equivalent Man, Rontgen being, I believe, the guy who went through and catalogued a whole bunch of different energies and damages that occur as a result of radiation damage. But the REM is the potential damage of the radiation dose to a human, specifically for humans now. No longer talking about other living organisms, just about humans. And it is that rad value, that energy per kilogram, adjusted by taking into account the type of radiation. As we said, alpha, lots of mass, lots of momentum, lots of kinetic energy, lots of damage. So it has a modification factor of 10. So it's the number of rads times 10 to get your REM for alpha radiation. For beta and gamma radiation, we just leave it as the rads. Right? So they just stay a factor of 1. So the REM is equal to the rads, and then the REM is just essentially just taking into account the fact that alpha radiation is going to be able to do more damage. So that's all REM is. If a person is exposed to 500 REMs in a short amount of time, they have a survival rate of 50%. 500 REMs in a short amount of time. That short amount of time is not really specified. Just remember that the longer it's spread out, the more chance your body has to try and recover and recuperate from that damage. So short amount of time, we're usually talking a few hours or possibly over a day or two. So there's no specific time frame, but the shorter the time frame, the worse, right? The worse off the person is going to be. If you get more than 1,000 REMs then you will be dead in a few days, right? That's just, it's going to happen. There's nothing we can do about it. Remember, this is radiation that is doing damage right throughout your entire body, right to the insides of all your internal organs. There's literally nothing we can do about it. If you are exposed to 1,000 rems, then you will be dead within days. Within 100 and 200 rems, 500 was 50%, 1,000 is certain, 100 to 200, pretty serious radiation sickness. There'll be vomiting, fatigue, weakened immune systems. There's all sorts of damage going on, but your body can often repair it. It is recoverable, right? It'll be horrible. You may have permanent damage as a result, but you will usually survive. 100 to 200 usually survive. But on the plus side of all of that, right, that all sounds pretty horrible and morbid, and it is. But on the plus side, we are usually only exposed to tiny, tiny amounts of radiation. The amounts we get in our daily lives are so small that the units millirem, mrem, are the general units that we use for radiation exposure. Right? We use millirem, thousandths of a rem. Remember that it was taking 100 to 200 rem, right, and 500 rem for a 50% chance. And here we are talking about millirem, thousandths of a rem. So worldwide, the average annual exposure is about 240 millirem. 240 millirem is 0.24 of a rem, so about a quarter of a rem. That's the annual exposure. That's how much one person gets in an average year. A whole year, they get a quarter of a rem, and we said that it takes 100 to 200 rem to get that illness, 500 to get 50% chance of death, and closer to 1,000 to get pretty much certain death. And our average annual exposure is a quarter of a rem, so really not a lot to worry about on your day-to-day life. This graph is from USA data, which is going to be different from what we experience in New Zealand or Australia or other countries. So do take this with just a grain of salt. It's just an idea of where this radiation can come from, but it's not going to be specific to each person. This is an average for American citizens. So about half of that quarter of a rem comes from background radiation. That's radiation that's just always present, which, as you can see by looking at the diagram, comes from terrestrial. That just means of Earth, so rocks and other things that have radioactive elements in them. They can provide some radiation. Internal, that means inside ourselves. So we'll talk a bit more about that in a moment. From space, that's cosmic rays. I already mentioned cosmic rays when I talked about transmutation of nitrogen-14 into carbon-14. Some of the particles and energy that comes in from space can make it to the ground, and that can affect us as well. And a lot of it comes from radon and thoron, depending on where you are in the world, as I'll mention on the next slide. The other big chunk is medical. The other half is medical, and that is from things like X-rays, CT scans, and a whole bunch of different practices that use radioactive particles in some way. Obviously, for people that get those procedures done, that's going to be a bit bigger, and for people that don't have it, that's going to be pretty much nothing. But the average is about the same as that background radiation in a standard year. And you'll notice the pink, purple, and orange slivers of pie up the top, which have been exaggerated to make them visible because they're tiny, or the consumer one's about right size, but the industrial and occupational should be a lot smaller. That is from just industrial and occupational. As per the names, they come from exposure through workplaces and through industrial fabrication and processes and goods, services and stuff that you might encounter. Consumer is the products that you end up receiving. So things like smoke alarms. Smoke alarms have radioactive particles in them. That is how they detect smoke. So they are all present, they all contribute to our annual radiation, but our annual radiation intake, as I said, is a quarter of a rem, and we need hundreds of rems to start getting radiation sickness. So no danger in a standard human's life. It's only when you start dealing with things that are specifically radioactive, so if you're doing research or if you're working in nuclear power plants and so on. Naturally occurring radioactive materials exist, as we've talked about. They are formed and then they get used to make stuff. We've got carbon-14 in us, etc. But the most common one on Earth, the most common radioactive material that causes risk for humans is radon-222. And that is part of the decay chain of uranium. Remember decay chains from the previous lesson. Part of that is radon-222. The amount of radon-222 that you're exposed to depends on your location on the globe. The amount of uranium in the natural earth formations, and therefore the amount of radon that is occurring, that is present, depends on where you are on the planet. For us here in Australasia, it is practically nothing. It is very minimal. There's definitely some, but it is minimal, not a risk. In places like America, it's a bit more of a risk. In places a bit lower, so Mexico and in that continent, getting more of a risk. But as you can see from the graph, there are various regions around the world where it's a bit more of a risk, and various regions where it's not much of a risk. It depends entirely on the natural terrain, what it's made of, and how much uranium there was present in it at some point. The other thing about radon is that it's a gas and it's heavier than air, so it will fill up things like basements. So especially if you have basements and you're living in one of the danger zones, then there is a very real risk of radon building up in that basement and providing a significant source of radiation damage and thus health risk. But as I said, in Australasia, not much of a problem. In other countries where it is a problem, radon detectors are pretty common. Just like we have fire alarms or smoke detectors, you get radon detectors and you just install them in risk areas like basements. Non-natural radiation, as I mentioned, is mostly from medicine, but occasionally small amounts from industry and other activities. And it's between 20 and 50% of your radiation exposure, depending on where you live. It may be more if you're getting less of the natural radiation from things like radon, so it may account for more. It is interesting to note that coal power plants are actually far worse for radiation damage than nuclear power plants are. So coal power plants already have this bad image of being dirty, right, contributing to global warming, and they certainly do, and for that reason alone we should stop them. But people are afraid of nuclear power plants because of the word nuclear. They don't really understand what it means, and they're just afraid that there is this risk of radiation to just the general population. But that is not present. That is one of the risks that is not there for power plants. Not in modern power plants anyway, obviously. Some of the older ones that didn't have the same safety protocols and caused meltdowns like Chernobyl, they caused issues, but the modern safe power plants do not cause issues. They are one of the cleanest methods and safest methods for energy creation. I use that word cautiously because I've already said you can't create energy, but converting nuclear energy into usable energy for humans. The reason is that coal power plants, they combust coal, and that releases smoke and particles into the atmosphere, and some of those particles are radioactive. So radioactive elements get released into our atmosphere, and then we can absorb them, we can inhale them or ingest them, and then they decay. And as we said, decaying radioactive stuff inside us is the worst, right? Alpha inside us is the worst. And that can happen with coal power plants as part of the smoke and smog that they release. Nuclear power plants, yes, there is a lot of radiation going on. That's where the energy comes from. We capture the energy from that radiation, and they do create radioactive waste. They do create waste products which are radioactive, but they are creating waste products that are radioactive that we can contain. We collect them, and then we can handle them safely and ensure that they do not present a risk to humans, right? Putting them in locations where they are not exposed to humans, or where they're in lead-lined things so that the radiation can't get out, things like that. So there is more radiation involved in a nuclear power plant, but it is a lot safer because it is contained and controlled, as opposed to the coal power plant, which just spews it out into the atmosphere. So coal power plant's bad on many, many fronts. That said, energy from solar and wind is obviously our best choice because it doesn't have any of those risks. But I'm getting off track a little bit. You don't really need to know about all of the stuff I was just saying about coal power plants. That was more of a sidetrack because I find it interesting, and hopefully you will do as well. Specific radiation sources. How much radiation do you get from these procedures? For a whole body CT scan, you get about 1,000 millirem. 1,000 millirem, that is 1 rem. So a whole body CT scan, you're only getting 1 rem. One. Takes 100 to 200 to start getting serious radiation sickness, and here we're talking about 1 rem. 1 rem, and I mean, unless you're getting 100 whole body CT scans in a day, not a problem, right? Upper gastrointestinal X-ray, 600 millirem. Head CT scan, 200 millirem. high altitude annual cosmic radiation. Remember I said cosmic radiation, stuff coming in from space, in through the Earth's atmosphere. Some of it gets down to us on the ground level, on sea level. If you are up a mountain, then there's less atmosphere above you and more of that radiation can actually get to you. So you'll see that is 80 millirem, and a couple of lines down you've got low altitude cosmic radiation of 30 millirem, and that's annual. That's for the whole year. 0.08 of a rem, 0.03 of a rem, depending on your altitude. A mammogram, 42 millirem. Annual radiation from inside your own body, 29 millirem. Terrestrial annual radiation, so from the ground up to us, 21 millirem. A chest x-ray is 10 millirem, and living near a nuclear power station annually is not measurable, right? It is less than a millirem, right? Less than a millirem. Don't memorize them, don't even bother writing them down unless you find them fascinating. The point is there's a huge range and they're all low. Everything that you encounter in your daily life, low energy, low radiation risk. The one that's very interesting, though, off that list is living organisms containing radioactive materials and the damage we receive from that. We already talked about this idea of carbon dating, radioactive carbon that is always inside us and it's inside every living thing, and that's how we can tell when things died, how long ago it died, using carbon dating. So that is one source of risk, but the other one, there are more, but the primary one inside us, carbon dating, is half-life of 6,000 years, not really going to be happening a lot and not a huge danger to us. But the one that is the most noticeable inside us is potassium. Potassium has about 0.01% of all its atoms being radioactive, and the average human is, by mass, around 0.4% potassium. So the radiation received from this potassium averages around about 29 millirem in a year. 29 millirem in a year. 0.03 of a rem per year just from the potassium inside us. I've included a picture of banana because that is obviously a common source of potassium, but of course there is potassium in a lot of different things and we get it from a lot of different sources. So just bananas alone isn't really a problem. The point is there is always this potassium inside us. There is always this radiation occurring, and it is always being fixed. It is always being repaired by our body. Our body just, if the cells die, it gets rid of them and replaces them. If the cells mutate, then it fixes whatever it needs to or ignores it if it's not a harmful mutation. And so it is just always happening. Because living organisms consume various substances, we can control this to a certain extent. We can deliberately make something absorb radioactive atoms. We can give them some substance, such as water, and we can include with that water some radioactive substances, some radioactive atoms that the living organism will consume. This happens with, the picture here is a plant. So we water a plant, we include some radioactive particles inside that water. As the plant absorbs the water, it drinks the water and spreads it out through its roots, but it absorbs it through the roots, up through the stem and out to the leaves and everything. We can use radioactive detectors, radiation detectors, to watch where the radiation is occurring. And that shows us where the radioactive particles are going and trace out the pathway of that water being absorbed by the plant. For that reason, these materials are called tracers, because we give them to biological organisms in order to trace out pathways. But along that line, there's a whole bunch of other things here. Humans get this. Humans will often be given radioactive injections or things to consume for the same purpose. We can follow along and check where that radioactive substance is by using a radiation detector and see where it's gone and follow those pathways. They do the similar things for sewer pipes and water mains and things like that. If there's a leak and they're trying to figure it out, then they just put a small amount of radioactive material into the pipe, and then they can use radiation detectors to see where it's coming out, and then they can dig up and repair the hole in the right place. So they don't use that all the time, but they are certainly tools that are available. Another very common use of radiation is to irradiate food. Food is already dead. Food's dead. It doesn't matter if we damage the cells in a strawberry from radiation. It's still a strawberry, it's still dead, it's still pretty much the same as it was before. When we consume it, it doesn't matter if a couple of the cells have broken open, we're still consuming all of the substance anyway. But the microorganisms living on the food are alive. They are alive, and they are the things that can cause mold and other rot. And so if we expose the food to radiation, then we can kill those little microorganisms and prevent the food from going bad, right? Because it was never the food that went bad, it was the microorganisms that killed that processed the food, right? That feed on the food. They are the things that cause the food to go bad. So if we can kill them, then the food will last a bit longer. The radiation being absorbed by the food doesn't result in the food itself becoming radiation. Right? If you get shot by a bullet, you don't become a gun. If you get hit by an alpha particle or an electron, then you don't become a radioactive particle yourself. Right? The strawberries do not become radioactive in any way. They absorb the energy. They may have an extra electron or helium nucleus in there, but so what, right? They're already full of protons, neutrons, and electrons. It doesn't actually affect them in any way. What it does do is destroy those microorganisms so that they will no longer reproduce and no longer consume the food and do their processes which make it go bad. Speaking of detecting radiation, let's talk a little bit about that. A lot of our uses need us to be able to detect that radiation, whether it is doing something like a tracer where we want to see where it has ended up, or whether it's for prevention and detecting radiation so that we can make sure that people aren't exposed to it. We want to be aware of how much radiation there is, so we need some way to detect radiation. There are a bunch of different approaches. I'm going to mention a bunch of them. You don't need to memorize them all. Remembering a name or two of them would be a good idea. Being able to remember the processes is the key. Right? The ideas behind the radiation detection is the key. So the Geiger counter is the movie method. It's the one that you see in TV shows and movies. And all it is a wire inside a hollow metal chamber. That hollow chamber is filled with a low pressure gas. If radiation enters, it ionizes the gas. Remember that ionization is removing an electron or adding an electron to an atom. What's happening here is that the radioactive particle is hitting the atom, giving the electron on the atom, one of them, enough energy to escape the atom entirely. Right? Remember, it's attracted to the protons in the nucleus, and that's why it stays in the atom, surrounding the atom. But if it gets enough energy, it'll fly away from the atom. And that's called ionization, removing an electron. So if the radiation goes in, hits the electron escapes, then it can go and hit a circuit, and it can complete a circuit. We haven't covered circuits. We'll talk about that in the next section, but it completes a circuit, and the circuit can be used to make something like a clicking sound or a light flash or something. The clicking sound is the common one in the movies, and so when there is radiation, it will click more frequently. Right? When there's very low radiation, it won't click, or very rarely. As it gets to a higher radiation, it'll start clicking more. So that's the standard classic movie radiation detector. Sometimes we're not so interested in whether there is radiation present in the environment, but we want to observe the radiation that comes out of a specific thing. So a cloud chamber is a good way to do that. A cloud chamber is a little chamber, so that is a closed petri dish type chamber. So it's a little plastic dish that we're looking at in that photograph. And inside that dish, there is water vapor that is saturated. And what saturated means is just that you can't get any more in. So water vapor is just gaseous water, but there's as much as can be in there. If there was any more, it would condense. Right? It would condense and form liquid water, so you can't put any more water vapor in. That's what saturated means. But when the radioactive particle emits radiation, that charged particle, alpha or beta, right? Alphas are helium nuclei, so they're positive. Betas are electrons, so they're negative. They pass through the vapor and they collide with the water vapor, and they leave a trail of ions. Right, so those are the atoms it's collided with and provided enough energy for ionization, just like we had with the Geiger counter method. So the atoms now that are in the water vapor atoms are now ionized. And the gases, the particles in the gas are ionized. The water vapor condenses around those ions, forming miniature clouds. We're not going to go into exactly why or how that happens, but all those little white trails that you can see in that photograph, they are tiny little clouds. They're little clusters of water vapor droplets in the air. And they are showing you the pathway of all of the little particles, the alpha and beta particles that came off that radioactive substance, which is on the end of that little metal rod there. So cloud chambers are ways for us to visualize the radiation coming off something when we have it in that specific environment. Bubble chamber, I'll be a bit quicker about this one. It's exactly the same idea as the cloud chamber, but instead of taking water vapor and turning it into condensed water droplets, it's going the other way and using liquid hydrogen and using the radioactive particles, the radiation particles, the alpha and beta particles, to create trails of bubbles of gas. So it's pretty much the opposite, right? Trails of bubbles through a liquid instead of trails of liquid through a gas, right? Other way around. There's a bit more detail on that slide if you want to read it about exactly how it works, but that is the key point there. A spark chamber, very similar. We haven't talked about electric charge get, which is the next section, so this one might not make too much sense yet, but essentially, same idea again. The alpha and beta particles ionize the gas particles in between a whole bunch of metal plates. And wherever these ionized particles are between these metal plates, and these metal plates have been charged up, they've been charged up, which again make more sense in the next section, they will discharge and they will create a little spark from one plate to the next. And that little spark will occur wherever the ions are, which is wherever the alpha and beta particles have been. Scintillation chamber is the emission of light by easily excited substances when exposed to charged particles or gamma rays. Scintillation just means tiny flashes, tiny light flashes, that's all it means. It is more sensitive to gamma rays than Geiger counters, and so it can provide information regarding the energy of the charged particles or gamma rays being absorbed. So again, same sort of idea. Right? Same idea that you just trace out the path of the particle by some effect it has. In this case, it uses a material which gives off little light flashes when it receives this extra energy from the nuclear radiation. So that was a little section on radiation detection. What you'll hopefully gain from that, so I'll just go back because I'm not talking about part 5 yet. What you'll hopefully gain from this discussion of the different types of Geiger counter, cloud chamber, spark chamber, scintillation chamber, bubble chamber, all of those, what they're doing, you are never seeing the radioactive particle, not radioactive, the radiation particle, the alpha, beta, gamma, X-ray. You're never seeing any of the actual particles. What you're seeing is their pathway. In the Geiger counter, you're not even seeing the pathway. You're just getting an indication that it's there somehow, right, from a beep or a flash. For all the other ones, you're seeing the pathway. You're seeing the pathway because those particles are very high energy. They can ionize the substance that they're traveling through, and that can do different things. It can form a cloud or a bubble or a spark or a little tiny light flash. And so you see the pathway, which is just the effect, right? So it's like looking at the footprints of the radioactive radiation particle as it travels through the material. This last part is the last part of this lesson. It's also the last part of the radiation, the nucleus, the atomic structure section as a whole, and it is on fission and fusion. So it's going back to the idea of the atomic structure of the nucleus, right? I said atomic structure, the structure of the nucleus. Recall that the nucleus is made as positive and neutral particles. We've got protons and we've got neutrons. They're held together by the strong force because all of the positive protons are all repelling each other. The electric force, though, is weaker than the strong force. So as long as we have enough neutrons, enough glue, the nucleus will hold together as one big lump. But sometimes there is just too much electric repulsion and an alpha particle is emitted. That's what we've already talked about. Sometimes there's too many neutrons, too much of the glue, and one of them will just convert to a proton. So we already talked about that. But what about when the atomic nucleus gets beyond that, gets even bigger than that alpha and beta particle decay sort of status? Plutonium, with atomic number 94, is actually the largest element that can be found naturally. All of its isotopes are radioactive. Right? There are no stable isotopes of plutonium, but some of them have very long half-lives. Plutonium, I forget which, I haven't written which isotope, and I've forgotten which one it is, but one of the isotopes has a half-life of around about 80 million years, and so that means that it can still exist for a long time. It will eventually decay, but it can exist for a long time. But it's right up there. It's right on the border of being too big to be stable for even any amount of time, and so they're all radioactive, all versions of plutonium. Any higher atomic number, any more protons than 94, and it just won't stay together long, even with heaps of neutrons. Even with heaps of neutrons, there is just too much. 95 protons is too many in a nucleus. Elements which are higher in the periodic table, they have still been studied because they can be created in labs. We can create these elements. Americium, or americium, I assume it's americium, has 95 protons. Right? It has a half-life of between 141 and 7,370 years, depending on which isotope it is. So it can still be created, and it can still exist for a while. But if it was created in a star, as all the other atoms that we ever encounter are, naturally created that we encounter, it would decay before it ever became part of a planet. That's not long enough for it to be ever used in creating a planet or anything else. So anything larger than plutonium won't exist. But remember, the longest lived plutonium isotopes have a half-life of 80 million years. So that means after 80 million years, you've still got half of it. After 160 million years, you've still got a quarter of it. So you can easily get plutonium that is still in existence from natural formation in stars. The highest atomic number that we've ever created, I say we, I was not involved, that has ever been created is 118, and they named the element oganesson. It's believed to have a half-life in the region of milliseconds, but because they've only ever created 5 or 6 atoms of it, it's hard to say with any certainty what the half-life is. You need to study a lot of atoms, a lot of radioactive decay, to get an actual estimate of the half-life. So they think it's in the region of milliseconds, but they can't be certain until a lot more atoms are created and studied. Uranium is right on the border of being too big, right on the border. Plutonium, as we saw, is too big. Uranium is right on the border. The isotope uranium-238 has a half-life of around 4.5 billion years, about the same age as the Earth, right? About the same age as the Earth. If it's left long enough, it will undergo alpha decay, lose a couple of protons, become a different substance, as we saw that whole big decay chain that takes 4.5 billion years. It will happen, it's slow, but it still can last for a while. But the other thing that can happen with uranium is that the nucleus can be deformed slightly. There are a variety of different reasons for it to be deformed, but if it gets deformed, then all of a sudden the nucleons are not actually going to be neighboring as many as they were before when it was perfectly spherical. When it's perfectly spherical, you get the most amount of strong force that you can. As you squish it and become more oval shaped, as you become more oval shaped, now you're getting less strong force interaction overall. But the electromagnetic repulsion is not really changing much, because you've still got all of its protons all within the sort of same region of each other. So you get the same repulsion, and now you reduce the strong force slightly. And if you reduce the strong force enough, you get to a point that's called critical deformation. Then the strong force is no longer enough to hold that nucleus together. And what will happen is not alpha or beta decay, but is nuclear fission. The entire nucleus will just break into 2 parts. Right? It will break into 2 parts, and the nucleus is now 2 separate nuclei, 2 different atoms. So that point, critical deformation, if it reaches that point, you can't go back. It is going, the electromagnetic repulsion is going to win, and the nucleus will split in half. So critical deformation, as per the name, critical, it will split. The result is 2 smaller nuclei, 2 smaller atoms. Now, this doesn't just happen with uranium. I'm using uranium because that's the most common example. It's the one that we have, humans have caused. They have caused nuclear fission in the atomic bomb. The result is 2 smaller nuclei, 2 smaller atoms. Right? Each atom now has a smaller nuclei than that one original one did. But a lot of energy is released. Remember E equals mc squared? Right? Remember that, I can't remember if I included the graph. I haven't included the graph. Actually, I'll go to my document camera. Remember the graph we had, the idea of the number of atoms, or the atomic number, and the mass per nucleon. That was what we talked about with E equals mc squared, and we said that hydrogen has biggest, we had iron with the lowest, and if we went either way, then it sort of went like that. And if you've gone and you've taken uranium, which is up here somewhere, and you split it into two particles which are down here somewhere, then you've got a lot less mass per nucleon, right, for both of them, which means overall you've lost a whole bunch of mass. And where does that mass go? It goes into energy, E equals mc squared. So when that nuclear fission occurs, then a lot of the mass is turned into energy, and you end up with a lot of energy being released, and that is why you get explosions and things. Right? So this process is called nuclear fission. If you need help remembering that, fissure means split or crack. Fissure means split or crack. So nuclear fission is the splitting of the atom. You can cause nuclear fission by hitting a nucleus with something with a lot of energy, like an energetic neutron. So if you fire one fast traveling neutron into a uranium nucleus, then it will form that, cause that nucleus to deform. It will sort of spread it out, kind of like if you hit a ball of putty right in the middle with a little BB or something, it would sort of flatten that ball a bit, it would spread it out a bit. The same thing happens here. You hit it with a highly energetic neutron, then it will sort of spread out, and usually, a lot of the time, it will reach that critical deformation point, then it will split in half. In this case, we have Kr krypton probably, and Ba barium maybe. I'm not good at my atomic symbols, so I apologize if those are incorrect, but it splits into those two. It also gives off some more neutrons. You'll see 3 neutrons being released. So 1 neutron into a uranium nucleus causes it to split into these 2 smaller nuclei, as well as releasing a bunch more neutrons. That decay equation down the bottom, exactly the same as the other decay equations in terms of balancing it. They have included the extra step of the big nucleus with that extra neutron in it, so the 235 uranium becomes 236 uranium for a moment as it deforms and splits, but you don't even need that middle step. The point is that in uranium and neutron and out, you've got the 3 different things coming out. You'll notice when we've got multiple neutrons coming out, we write them as just the 3 out the front, saying we've got 3 of them. So it's pretty basic math there. But the exact same process, I think I may have included a couple of decay equations for you to do that again on the worksheet. When that happens, when a uranium nucleus receives a neutron, deforms, splits, and gives off 3 more, you now have 3 more energetic neutrons that can go off and hit another nucleus. And then each of those will deform, give off 3 new neutrons. So the first one gives off 3, the next, if that, say 2 of them collide, you've now got 6 neutrons. Say 4 of them collide, you've now got 4 times 3, you've got 12 neutrons. And so you get a chain reaction, this growing in the number of neutrons that are flying around inside the sample of uranium. Because of course you never have a single uranium atom, you've got a sample with a whole bunch of uranium atoms. And so you get this chain reaction. And every one of those fission reactions, those fission decays, every uranium nucleus that decays into 2 other nuclei gives off a whole bunch of energy. The chain reaction means that expands rapidly, exponentially. We get heaps and heaps of them, and pretty soon the entire uranium sample has all changed. It's all undergone fission, all become other things, and released a huge amount of energy. Right, so huge amounts of energy can be released from a chain reaction of nuclear fission. So how do we stop that occurring until we want it to? Right? How do we have a sample of uranium-235 that doesn't just spontaneously undergo this chain reaction? And you can't say don't give it a neutron, because there are enough uranium atoms in the sample that one of them might spontaneously just undergo fission and start the chain reaction. So that's very dangerous. You can't have that. What you can do, though, is keep the lump of uranium small enough that the neutrons that do get released when one spontaneously undergoes fission are more likely to leave the sample than to hit another particle. So I'll go back to the document camera for a moment, just to hopefully try and make clear what I mean by this. Remember that our atoms are huge and the nuclei are the size of a pea in a football stadium. So we've got a sample of uranium. Here's a whole bunch of uranium atoms. They're all stuck together. They're all big full atoms, but the nuclei are tiny, right? Nuclei are these tiny dots. This is nowhere near to scale because that's not the size of a pea in a football stadium. But if you've only got a few of these uranium atoms and one of them spontaneously undergoes fission, right? So this one undergoes fission and splits in half, and it gives off 3 neutrons, right? Gives off 3 energetic neutrons, but they can just leave, right? They won't hit anything on the way out. So if you only had 8 uranium atoms like that, you'd be very, very unlikely that if one atom underwent fission, any of the others would as a result. If you get up to a few hundred atoms, you might occasionally get one going off as a result of a neighbor going off. As you get bigger and bigger, it becomes more and more likely. Right? If this has to suddenly travel through not just these, but it has to travel through thousands of these atoms that stretch off into the distance before it gets out of the sample, then it's very likely along the way to hit one of those nuclei. So the bigger the sample is, the more likely that chain reaction is to occur. Hopefully that all makes sense. If the sample size is large enough, most of the neutrons will collide with other ones and we get that chain reaction. The sample size at which that is going to occur is called critical mass. Right? So we had critical deformation, the amount of deformation we needed for that fission to definitely occur. Critical mass is the overall mass of the sample of uranium that we need in order for that chain reaction of those fission reactions to definitely occur. Sometimes called the critical amount, but critical mass is more scientific because we've got a mass of uranium. How then do we make a nuclear weapon where it only experiences the chain reaction when we want it to? We just have multiple lumps. You have smaller lumps, so you get a lump of uranium that's only 1/10 of the size of the critical mass, and you get 10 of them, and you keep them all in separate little chambers, and then when you want it to explode, you push them all together and create one big lump that is bigger than the critical mass or the same size as the critical mass or bigger, and then that will just undergo spontaneous chain reaction. You don't even have to give it a neutron because one of the uranium atoms will undergo spontaneous fission, and now that you've got a lump that's bigger than the critical mass, then that chain reaction will occur. And that's what a nuclear explosion is. A nuclear explosion is the spontaneous chain reaction due to a lump of uranium that is bigger than the critical mass. Don't go trying to make that. I'm a pacifist, so I don't encourage the use of nuclear weapons, not that you would have much of a chance of doing that anyway, but it's still very important to understand the science behind them and how they work. The other side of that coin, nuclear fission, splitting an atom in half, the other side of that coin is joining them together. We've already actually talked about this because we talked about it in stars. Stars are big and dense and hot and lots of pressure, and they can force nuclei together. When 2 nuclei are forced together and joined to create a bigger nuclei, it is called nuclear fusion. Right? So nuclear fission was the splitting, nuclear fusion is the joining. And again, using E equals mc squared, this can also release a lot of energy. If the 2 atoms are smaller and they create a bigger atom, bigger nucleus with less mass per nucleon, then it can release a bunch of energy again, right? We can lose some mass, gain some energy. And so if humans could control fusion, if we could cause fusion and sustain a fusion reaction, we would have plentiful energy because we could just take a whole bunch of hydrogen, take a whole bunch of helium, whatever we have access to, and we could fuse it together, create bigger atoms, and create a whole bunch of energy. It would be limitless energy, essentially, for our purposes. That is very difficult to do. Fusion reactions are starting to be controlled. I believe there was some news recently about sustained fusion reaction for a little while, but still not on the sorts of scales we need to have industrial fusion power plants. And that's it. That's the end of our section on atomic structure and on nuclei. I didn't mention actually fusion. Hopefully you can remember fission and fusion, but fusion, I said fission, splitting, fusion, fuse, so joining, fusing 2 things together. So nuclear fusion is from that. So that's the end of atomic structure, which included nuclear structure, nuclear radiation, and damage to us, and so on.